Hi, my name is Meghana Chamarty, and I am a part of the Research and Chemistry program at the North Carolina School of Science and Mathematics. I researched the selective and cost-effective depolymerization of linear polyethylene via a tandem dehydrogenation and metathesis dual catalyst system. Being very inexpensive to produce and composing many single-use commodities, polyolefin waste is abundant, making up about 57% of the 380 million tons of plastic waste produced annually. While the strength and versatility of polyolefin plastic is the reason why polyolefin products are so useful, the sp3 hybridized nature of the carbon-carbon bond between monomers of the polyolefins causes them to be highly resistant to biodegradation. As a result, plastics can take hundreds of years to naturally decompose. Efficient methods to aid in the safe degradation of polyolefins is much needed to prevent harming the ecosystem and negatively affecting the natural environment. Currently, the plastics recycling economy is a linear system. Each step in the linear plastics economy is energy-intensive, produces waste, and can only be utilized in the production of lower-quality materials, making this process highly unsustainable. A better approach to recycling is to convert the polymetric material back into starting product so that it can be used again as raw material. This approach is referred to as the circular recycling process. An efficient method of recycling that can transform the polymer structure of plastic polyolefins into small monomer alkanes will allow for the plastics economy to be transformed into a circular recycling economy. This will result in increased efficiency, decreased loss of energy, decreased environmental harm, and increased overall sustainability. Current methods of recycling polyolefins can be categorized into three broad groups: mechanical recycling, thermochemical recycling, and catalytic recycling. Mechanical recycling is the current method of mass recycling, although it is extremely inefficient with only 16% of plastics actually getting recycled. Additionally, recycled plastics have limited uses, so this method is not sustainable. Thermochemical processes require high amounts of energy and have low product selectivity. These processes, which include pyrolysis and thermal cracking, enable the depolymerization of polyolefin by carbon-carbon bonds and polyethylene to produce lightweight liquid alkane for fuel sources or integrated into chemical refineries. However, these processes are energy-intensive and lack product selectivity. Catalytic recycling of polyolefins, unlike mechanical and thermochemical recycling, can selectively cleave the carbon-carbon bonds in an efficient manner. This method has been studied for short-chain alkanes and lignin, but has not been extensively explored for the depolymerization of high-weight polyolefins. Recent literature reported a mild and efficient degradation of polyethylene into liquid fuels and waxes using light alkanes, an iridium-based pincer-ligand dehydrogenation catalyst, and iridium oxide / aluminum oxide metathesis catalyst. Alkane metathesis is the process by which alkanes are covalently rearranged to give a new distribution of alkane products. Their research demonstrated high efficiency, mild reaction conditions, and fine control over degradation products, showing distinct advantages over traditional pyrolysis processes. However, expensive and toxic metals such as iridium are at the core of the catalysis method. Therefore, if utilized at larger scales, their proposed catalyst system would pose environmental and health risks. My research shows the tandem metathesis and dehydrogenation catalytic depolymerization of linear high-density polyethylene to processable lightweight liquid and midweight waxy hydrocarbons using relatively safe, cheap, and abundant cobalt in a metallo-pincer ligand. This method of polyethylene degradation is based on a tandem catalytic cross-alkane metathesis process, which involves one catalyst for alkane degradation and another catalyst for olefin metathesis. The catalyst of particular focus for this research study was the alkane dehydrogenation catalyst. First, a novel one-step synthesis pathway was developed. Then the synthesis pathway was tested and proved. Finally, polyethylene recovery and dehydrogenation activity was investigated as a function of conversion. The class of pincer complexes has been studied as the applications for catalysts in many ways. They promote pathways such as Heck and Suzuki coupling, allylic additions, and reduction of carbon dioxide. Pincer complexes are characterized by coordinate bonding that binds tightly to three adjacent coplanar sites. I optimized an iridium pincer catalyst complex by removing the tert-butyl phosphine groups on the benzene and substituting the iridium with first-row transition metals, nickel and cobalt. Pincer complex synthesis generally requires a standard two-step synthetic protocol that requires equivalents of base to remove 3 equivalents of acid generated during ligand synthesis and a metallation step. Requiring tedious precision and filtration, this process is time-consuming and difficult. Utilizing a similar one-step synthesis pathway, I adapted its procedure, substituting chlorodiisopropyl phosphine with ditert-butyl chlorophosphine to achieve the desired ligand. Then the procedure was adapted to the metals of interest, cobalt and nickel. This procedure can be seen in the flowchart on the side. A very similar procedure was used in the synthesis of the nickel catalyst. To test the catalysts, high-density polyethylene, nickel or cobalt pincer catalysts, rhenium oxide catalyst, and octane or decane were reacted in a 25 milliliter Teflon chamber in an autoclave and set in an oven at 175 degrees Celsius for 4 days. After 4 days, the contents of the autoclave were centrifuged, and the resulting pellet was decanted, vacuum-dried for 48 hours, and masked. The contents of the nickel reaction flask were initially gray or black. However, upon immediate addition to the flask, the nickel turned blue. After 5 to 10 minutes in the stir plate and the heat bath, the mixture became emerald green. At the conclusion of the 24-hour reaction, the mixture was more condensed. After 18 hours of normal evaporation, 0.866 grams of catalyst was collected and analyzed through FTIR. Due to the absence of the OH peak and an evidence peak in the aerofunctional zone, the nickel catalyst was concluded to have succeeded with a 38% yield. Similarly, the contents of the cobalt flask were initially gray and black. However, upon immediate addition to the flask, the cobalt turned blue. Contents of the flask were purified through crystallization. Purity was evaluated with thin layer chromatography using a 10% dichloromethane and 90% methanol solution. Contents were dried and stored in inert conditions. Due to the absence of the OH peak and an evident peak in the aerofunctional zone, the synthesis was concluded to have succeeded. Polyethylene recovery refers to the mass of polyethylene remaining in the sample at the conclusion of testing. Percent recovery is determined in comparison to control number 1, no catalysts. Normalized polyethylene loss quantifies the loss of polyethylene in the recovered sample. Because of the low molecular weight of the polyethylene, the smaller hydrocarbons converted by the catalyst are either dissolved in the decane or in the liquid state. Qualitatively, there was a visible color change in the dehydrogenation plus metathesis catalyst samples that was not present in the controls. Rotor vaporizing the liquid component of the cobalt catalyst sample, the decane rolled off, although there was still liquid left in the flask. This indicates that some of the polyethylene was degraded to smaller liquid at room temperature hydrocarbons, 10 to 16 carbon alkanes. This did not occur in nickel catalyst trials. Based on the results of these trials, there is considerable evidence for the successful degradation of polyethylene by the cobalt pincer dehydrogenation catalyst. Converting 27% of the polyethylene into light to mid-weight hydrocarbons in 96 hours with 28% recovery, this catalyst shows promise for mass-scale depolymerization of polyethylene at mild temperatures and pressures. In this work, a novel cobalt pincer dehydrogenation catalyst was developed to depolymerize linear polyethylene via a tandem dehydrogenation metathesis catalyst system. In contrast to previous work, this catalyst is cost-effective, non-toxic, easy to synthesize, and functions under mild conditions. The cobalt catalyst system is an important step in developing an efficient method of recycling that can transform the polymer structure of plastic polyolefins into smaller monomer alkanes, resulting in decreased loss of energy, decreased environmental and humanitarian harm, and increased overall sustainability. Future directions include computationally developing and screening more variations of these cobalt pincer complexes, computationally determining the mechanistic model of the tandem dehydrogenation metathesis catalyst system, developing non-toxic metathesis catalysts, testing the catalyst for recyclability, and characterizing products with mass spectrum to precisely quantify the product distribution, analyze selectivity, and determine how selectivity behaves over various reaction time durations. I would like to thank the Burroughs Wellcome Fund, NCSSM Foundation, for making this experience possible, and my mentor, Dr. Tim Anglin, for his dedication and continued academic support.